So friends, it's to recall that we wanted to know under what conditions on a linear transformation its matrix with respect to some ordered basis is of a particular type. And in this context, we begin with the nilpotent linear transformations. And we said a linear transformation is nilpotent if its sum power is 0. And if k is such a least, say t power k is 0, but t power k minus 1 is not 0, then k is called the nilpotency index of t. Now, about nilpotent linear transformations, they are very nice transformations because they have many interesting properties to start with. So, for example, you can prove that all of its characteristic roots are 0. And since 0 belongs to the field, and therefore it is always triangulizable. What more than that can be said from the last lecture? That if all the characteristic roots of T lie in F, then we have proved that such a linear transformation is triangulizable. We also proved that it satisfies a polynomial of degree n, and this polynomial was x minus lambda 1 times x minus lambda 2 and so on, x minus lambda n, such that these lambdas are characteristic roots. Correspondingly, we also proved that the matrix with respect to an ordered basis will be triangular, and on the diagonal, the entries will be the characteristic roots of T. So if T is nilpotent, in that case, its diagonal will be 0 because every eigenvalue of T is 0. So what it turns out to be that there is a basis with respect to which the matrix of T is strictly triangular. We have called triangular here for lower triangular matrices, but the same can be done as the upper and lower triangular matrices are similar. Okay, so we wanted to prove more than that. So not just that it is strictly triangular. In fact, we can prove that there is a basis with respect to which the matrix is a diagonal matrix, but this diagonal consists of matrices themselves, A1, A2, AK, where AI is the matrix of Ti, and Ti is the linear transformation that is obtained by restricting T to the component Vi. Now, this Vi is their direct sum is V. And such a matrix can be obtained. And the sum of the dimensions of Vi is n. So an n by n matrix can be obtained, which is diagonal. And the diagonals having entries have matrices themselves. And these matrices are actually the restrictions of matrices, restrictions of the linear transformation T on the components V. All right, let us prove this interesting result as follows. So the proof. Definitely this k will not exceed n. Because if you have t to the power n as 0, and n minus 1 not 0, then this n, the nilpotency index, will not exceed the dimension of the vector space. All right, now let us begin with. So recall the statement: if V is the direct sum of the subspaces V1 plus V2 plus V3 plus Vk, where each Vi is of dimension Ni and is T invariant, since dimension of V, say n, is finite, and therefore the dimension of each subspace will also be finite. Let us call it, say, Ni is also finite. And since V is their direct sum, and therefore n is the sum of these ni's. Okay. All right, next let us take Bi to be the basis and say this is Vi corresponding to I, I, and this. So this is say basis for Ni, so it will have Ni number of elements. So 1, 2, and so on. So this will be Ni. So this be a basis for Vi for each I 1 to k. Now V1 is the basis for V1. The elements are V1 1, V2 1, Vni 1. So this upper is to denote corresponding subspace Vi. So these are k bases in number, like that. Now think of this B, which consists of all these elements and in the same order as well. So let us say this is here 1, and then you have here 1. Say this is also 1, and this is 1, 2, and then n1, and then you have more here for say 2. And 2 in number the elements. And the last that you will have here that way, corresponding to kth. So this is 1. This. So this has the number of elements. Naturally, the number of elements so here will be n1, n2, and so on, nk, which is same as n. And I leave for you as a small, simple exercise that this B is actually a basis. for V over F. So once we have this as a basis, we can also observe about these subspaces Vi, that Vi is T invariant, and therefore each VIT is in Vi. Since each Vi is T invariant, what we get is VIT is contained in Vi for every I 1 to K. This is also given to us. So if you see this every element, so this Vji, each is in Vi, and so for the basis vector Vj, I, jth vector in the basis Vi of Vi in Vi, so this is in Vi. Vi. And this therefore under T will still remain in the linear span of Bi. So this Vji, and then if you take T of this, so this belongs to, so this is contained here in VIT. So this belongs to VIT, and VIT is contained in Vi, and this is the linear span of Bi. That means this Vji is in the linear span of the basis of Bi. Basis of Vi, which is Bi. So what is that? So it's Vi1, Vi here 2, Vi, and this is Ni. And that happens for every I 1 to K, and for every J corresponding to 1 to Ni. 1 to I corresponding to that. So this is in the linear span. Now once this is in the linear span, so what we see here, that this can be written as, so this means that this okay, so this Vjit actually. So for example, so when you take this as V11, so this V, and then here 1, and then here let us say 1, and T of this, for example, I is 1, J is 1. So this is the linear span of V11, V21, Vn11. So let us take, so this is A11, 1, A12, 1, and this is A1 and 1, V. One, V and 1, 1. So this can be written as the linear combination of elements from B. These will be the coefficients of V11, V1, V21, and Vn11, and the remaining coefficients can be treated as 0. So this can be written as A11, V11, A12, V1, A1N1, and this is just this one is not on this. Okay, Vn1 1 plus 0 here of V1 2 when the elements are coming from V2 plus 0 V2 and this is 0 V and 2 and like this 0 V from the kth subspace when it comes 1 0 this 0 V and K. This is Kth. So this is the linear combination. And therefore, hence the first row, this will give the first row of the matrix of T with respect to the ordered basis will be this A11, A12, A1N1, and then all the remaining entries will be zeros. First row of the matrix of T with respect to the ordered basis B is A11, 1, and you can say A121, A1N1, and all the remaining entries will be zeros. How many are the number here? So this is 1 by n, and n is n1 plus n2 plus nk. The first n1 entries will be like this. The remaining will be 0. Obviously, when you go up to n 1th row, then you will have here an1 Similarly, the n1th row of TB is, so here you will have the coefficient here of V1, 1, that will be A. Correspondingly, now you will have N1 because this will give you N1th row. So A1, N1, 1. A1, N1, 2. A, N1, N1, and correspondingly, because this is coming from V1, these will be the entries. And the remaining entries will be 0, 0, 0, and so on, zeros. This again is 1 by n. The next row will be interesting. So n1 plus 1th row will be what? N1 plus 1th row. So from where does it come? It comes when you pick up the n1 plus 1th vector from the basis, which comes from the subspace V2. So n plus 1th vector in the basis B is actually the basis, first basis vector of V2. That means of V2. So this will be, therefore, first n1 entries will be 0, 0, 0, 0, how many these will be? N1 in number. And the next will be here. So this coefficient will come and coming from V2, the first vector. So this will be 2 and this will be the first one here. So 1. So this will be coming in the n plus 1th row. So n plus 1th. So n1 plus 1, 1. Then again from 2. So n plus 1 plus 1 and this will be 2 and so on. And like that, this will come from 2. So this will be here n1 plus n. Oh, sorry, n plus 1. And this will go up to n. And then again will be zeros. And like that. So you can see that if the matrix if A1 is the matrix here, N1 by N1, A11, A12, A1 and 1, 1, A and 1, 1, A and 1, 2, 1, 1, A and 1 and 1. Like that. And if you do this for say I, so this will be the first matrix A1 and AI Ni by Ni. So this will be here ith. So this will start from, so this will be corresponding to I, and I, and I. But this will begin from your I plus 1th column. So this will be a I plus. So this is here. Plus 1th. So n I plus 1. That's where this entry will appear in the column. And row also will be Ni plus 1. So correspondingly, you will fill up here with the scripts. Then the matrix here TB will be naturally A1, A2, AK, and all other entries will be 0. And obviously, the way it has been obtained, this is also clear that Ti is the linear transformation induced by T on Vi. So Ti is the T on Vi. So Vti is basically V of Ti is 0 if V does not belong to Vi, and is Vt itself if V belongs to Vi. And in this setup, you can see that Ai is actually the matrix of Ti with respect to the basis Bi. So it proves a very interesting result about linear transformations. That the matrix with respect to some basis will be of this form. We want to see more of it. More of it means just more information about these matrices, AIs. Because what we know is that this is a block diagonal matrix, TV, but not much about AIs. So now we want to see, can AIs be of very specific nature? And indeed that is the case. So for this now let us see what can we do. So before that we prove a small observation. So observe that if T is a linear transformation in AFP, therefore V is finite dimensional, is nilpotent. So some power is 0 and this power cannot exceed the dimension that we know. Then any polynomial with non-zero constant term must be regular, must be invertible. Then any polynomial in T, so any polynomial in T, that means Qt, say alpha naught, alpha 1t, alpha m t m, with non-zero constant term is regular, is invertible. For this if S is a linear transformation, let us say here, is nilpotent of say nilpotency index say R, and alpha naught is not 0 element in F, then what we can see is that alpha naught plus S inverse will exist. Alpha naught inverse minus alpha naught, this minus 2 power means the square of the inverse of alpha naught S plus alpha naught s square minus and so on minus 1 to the power the r minus 1, and this is alpha naught minus r s to the power r minus 1. When you multiply, this will give you, so alpha naught, first you multiply throughout, then you multiply by s. So when you multiply throughout by alpha naught, this first one, so this will be 1 minus alpha naught inverse s plus alpha naught minus 2s square, and last term here will be minus 1 to the power r minus 1 alpha naught power, so this is minus of, so this is r minus 1, and this will become your power r. So alpha naught, let me write one term. Say minus 2. Alpha naught to the power will be r minus 1. R minus 1 because you are multiplying by alpha naught, and s to the power r minus 2. And the last term, that will be plus minus 1 to the power r minus 1 alpha naught. So this is here. This is r minus. So this will be power r, s power r minus 1. Just a second. This is alpha. This will be minus 2.
So it should be minus r plus 2, and at last it should be minus r plus 1.
Yeah. Minus 2 to the power minus 1. This will be minus 1. This will be s to the power s. Yeah. Okay. Now multiply by s. So this will be here your plus sign, so alpha naught inverse s minus alpha naught minus 2s square and so on minus 1 to the power r minus 2 alpha naught r minus 2 into s to the power r minus 1. And what will happen, the last when it is multiplied, that will be s to the power r, and since r is nilpotent of index r, that will vanish. So the last term will vanish, that will be the end of it. The last term being here, so minus 1 to the power here r minus 1 alpha naught, and this is r minus 1 as to the power r, that becomes 0. So you can say that there are plus and minus alternatively. So first term will stay and all other terms will cancel with each other. The last term stays and the first term stays. Last term becomes 0 because of this s to the power r. This becomes 1 plus minus 1 to the power r minus 1 alpha naught power minus r s to the power r. And this term is 0. Therefore, this becomes simply 1. Here 1 means identity linear transformation. So that makes that alpha naught plus s is invertible. This is regular. This is invertible and its inverse is also clear that this is the polynomial. And alpha naught plus s inverse is actually this polynomial. Alpha naught minus 1 minus 1 minus s s. क्या हो रहा है? Polynomial is alpha naught inverse minus alpha naught minus 2s plus 1 minus 1 to the power r minus 1 alpha naught minus power r into क्या लिखा जाए s to the power s चलिए यहाँ लिख लेना फिर. So is a polynomial here and alpha naught s inverse is inverted. Okay. So suppose t power r is 0. So if t power r is 0 is nilpotent and s is the polynomial say pt minus say alpha naught, that means excluding the constant term, so this is say alpha 1 t plus alpha 2 t square and say alpha m t m. So if t power r is 0, then s power r will be this is s. S power r will be power of this rth power of this alpha m t plus alpha m t m, and this will have factored t power r, so this will be 0. This is t power r will be a factor here s power r. So this s is nilpotent, and by the observation that we have just now made, this alpha naught plus s, which is pt. pt is alpha naught plus alpha 1 t plus so on alpha m t m, where we have assumed that alpha naught is not 0, is invertible. So we have proved this result earlier, that if t is a finite, t is a linear transformation or a finite dimensional vector space, then t is invertible or regular if and only if the constant term of the minimal polynomial of t is not 0. So we shall use this observation. Now let us have some notation, fix up this notation, say M. So we shall use this notation for a particular form of the matrix. So say M and say N is to denote the matrix N by N, and is of the form that this is 0, 1, 0, 0, and 0, 0. First row, second 0, 0, 1, 0, 0, 0, like that. And the last but one row 0, 0, 0, 0, and 0, 1. The last row zeros only, 0. So you can see that here all entries are 0 except the entries on the super diagonal, and all of these entries are equal to 1. So this is a matrix, so Mn has all of its entries 0 except the entries on its super diagonal and each entry on the super diagonal is equal to 1. So we shall fix up for the coming discussion the notation Mn for the matrix of order n by n of this form, that it has all of its entries 0 except the entries that fall on the super diagonal, and the entries on the super diagonal, all of them are equal and equal to 1. So what we prove actually, or wish to prove, is the following. So this theorem is what is the intention about the important linear transformations. So once again, let us take dimension of V or F be finite and say this is N. So if dimension of V or F be N finite, all our discussions are for finite dimensional vector spaces. And if T here is your nilpotent, then there is a basis. A basis, say B, with respect to which the matrix of T, that is this, is of the form, so this is n by n, and is again a block diagonal sort of matrix, and entries are m and 1, m and 2, and this m and k or r, whatever you want. All other entries are zeros. Even if I don't write the zeros, it means that they are zeros. You can also write these n1, n2, and k in the order that n r, and the sum of these ni's is the dimension of the vector space. So this is what we want to prove. All right, for the proof, now theorem is nilpotent, and let me have this n1 as the nilpotency index. Since it is nilpotent, and let me put of index and 1. Okay, since T is nilpotent of nilpotency index n1. So t power n1 is 0. T power n1 minus 1, this is not 0. So there exists a vector, let us say v, in v, such that v t n1 minus 1 is not 0. Obviously, v is not 0 because this would be 0 otherwise for any linear transformation. So there exists a v, and this v such that vt n1 minus 1 is not 0. Now you can take a b1, let us say. Also v1 is v itself, and v2 say vt, v3 as vt square, and so on. vn1 as vt power n1 minus 1. Now none of them is 0. Now each vi is not 0. You can prove that this is a basis. That means these vectors are linearly independent and they span. A subspace called V1. Anyway, so V1 is a linearly independent set. Then B1 is linearly independent, means so its elements are linearly independent. For you can take that linear combination, say alpha 1 V1, alpha 2 V2, alpha n1 V n1 0. That is so this is alpha 1 V. V1 is V, alpha 2 is Vt, alpha n1 is Vt n1 minus 1, and this is 0. All right, so this is the case. Now let us take S to be the least index, so that alpha s is not 0. So let S be the least such that alpha s is not 0. That means alpha 1, alpha 2 up to alpha s minus 1. All of these coefficients are 0. See, if all the coefficients alpha 1, alpha 2, alpha n1 are 0, then we don't have to do anything. That's what we want, that all will be 0. So suppose s is the least such that alpha s is not 0. But in that case, this linear combination reduces to the first term itself will begin from s. So alpha s, vts minus 1, and alpha s plus 1, and so on. So alpha n1, and this will be vt n1 minus 1, and this will be 0. because alpha 1, alpha 2, alpha s minus 1, all of them are 0. Now this s is naturally less than n1 and this. So this gives me that you can pull out this t power s minus 1 of v. So this v and this is t s minus 1. And here will be alpha s. This is identity. Alpha s plus 1 t. Alpha n1 t power n1 minus s. And this is 0. Now alpha s is not 0. And this is a polynomial in t. And t is nilpotent. What just now we have proved? That this must be invertible. Polynomial with non-zero coefficient in t is invertible. So this is invertible as a linear transformation. And this will force that v t s minus 1 is 0. Now s is s minus 1 definitely is less than n1 minus 1. This is a contradiction. S v, so t power, because this happens for every v. S is less than 1. Hence, there cannot be any, hence no alpha s is not 0. And that means each alpha I has to be 0. So what we have got is that v1, which is vt square vt n1 minus 1, where n1 is the nilpotency index, is a linearly independent set of vectors. And call this subspace spanned by this linearly independent set V1 as V1. So now let us take V1 to be the subspace spanned by V1. Subspace of V spanned by B1. You can see that the number of elements in B1 are N1. V, Vt square, Vt, N1 minus 1. So the dimension of, therefore, of this V1 over F is N1, and this is definitely less than N, and it's finite. The subspace is T invariant. You can note that V1 is T invariant for any element in the basis is of the form, for any, say, U in V1 is a linear combination of these basis vectors. So is in the linear span of B1. So this makes that U is say alpha naught V plus alpha 1 VT, or so this is VT N1 minus 1, and this is alpha N1 minus 1. So when you do this UT, then this is alpha naught VT, and so on, alpha N1 minus 2V, N minus 2T, T plus alpha N1 minus 1, V N1 minus 1, this is T. This is TS. And this will be Tn. And this will be 0 because N1 is the nilpotent index. So this still remains in the linear span of B1, and which is actually V1. So this V1 is T invariant. Also, you can see that if T1 is the restriction of T on V1, then the matrix of T1 with respect to the basis ordered basis B1 is actually M n 1. Because you can see that if you want to write the first row, for example, V1 T1, this is V1 T. Because this is T invariant, so this will be same as V1T. V1T is the same as VT. VT here is V2. So this is V2. So this is 0 V1, 1 V2, 0 V3, and so on. 0 V and 1. So the first row, therefore, of T1 with respect to the ordered B1 is first entry 0, then 1, then zeros, zeros, and then zeros. So likewise, you can write the other entries also. So this and similarly other rows. First row, which is same as the first row of similarly other rows. And this is the first row. So what we see here is that the matrix of T1, where T is restricted to V1, the first row is 0, 1, 0, 0. Next, what we see here is we shall need something more also, before we actually prove this theorem. So next, so if U is an element in V1, and is such that u t n1 minus k. Such that u t n1 minus k. This is 0, where this k is less or equal to n1. Then u naught t power k is actually u or some u naught in 1. Now for this, that is the only observation we will be able to do today. Sorry, we have to wind up because there is Viva scheduled now. So I have to wind up today. So we shall prove this observation next time. So thank you very much for your kind attention.
Thank you, sir.